Morning, fifth years. Just wanted to run through a correction for the exam paper question that I gave you on Friday. So I'm just going to use the question here from Study Clicks and the marking scheme, nice and simple, just to run through and make sure that we're clear on what's happening. So first part asks about resonance. Resonance is a phenomenon that is associated with musical instruments. What is resonance? So that's all it's asking there is for the definition, and then it asks to describe an experiment to demonstrate resonance. Okay, so we can see first and foremost there, resonance is a transfer of energy between two bodies of the same natural frequency. So if you recall, we discussed that with the two tuning forks, and we had two tuning forks with the same frequency, one vibrating, one not, and when we stopped the first one from vibrating, we could notice or recognize that the second one starts vibrating, and that showed resonance happening in real life. And again, it asks to describe an experiment to demonstrate that. And the one I've just explained is the example that's given. So you can see 6 marks for your definition in 2 parts, and then we get 9 marks for describing that experiment. Okay, no diagram needed or anything like that, but it just gives you just gives us a quick example of how that's happening. So nice and straightforward, 15 marks, no messing whatsoever, nice and simple. So next bit then is the main calculation part, and it's based around one of the mandatory experiments that we talked about. A stretched string of a violin has a length of 328 millimeters and a mass of 0.126 grams. So that's important. We need those two things to work out the mass per length. The string emits a note of 660 hertz when it vibrates at its fundamental frequency. So we're to calculate the tension in the string and the speed of sound in the string. So again, the tension in the string is your mass per unit length, if you recall, which is that mu Greek letter. Okay, so we can just do mass over length, and you can see that it is 0.126 grams. So we change that into kilos, 0.126 by 10 to the minus 3 kilograms, and 0.328 is meters, because we're talking about 328 millimeters. So to put that into meters is that 0.328 there. So I just divide those in first and foremost to get your mass per unit length. Mass is on top, length is underneath, and we end up with that 3.84 by 10 to the minus 4. Now the unit on that should be kilograms per meter. Okay, the next bit then is based around getting the tension. So we needed that mu value to fill it into this formula. So the F is equal to 1 over 2L multiplied by square root of T over mu. So we fill in everything that we know. We know the frequency is that 660 that was given to us. We know, 660, sorry. We also know the length, which is that 0.328. We also know the mu value, which we just worked out. So we've worked out all of those things, and we have everything except for T. So first thing I would do is square everything to get rid of that square root, and then you could bring the mu over to the left hand side, bring the 2L over to the left hand side, and you should be left with just the T on its own, and you can multiply that out, and we end up with 72 newtons as our tension. Okay, so that's tension, a unit of force. The next bit asks to find the speed of sound in the string. So we've done everything that we need to do there, and then the speed of sound. Okay, so the next bit on that, you can see that lambda equals twice the length of the string. If you can imagine the length of the string, like we have shown before, would be a half of the full wave. When that starts to vibrate, you'd end up with a bow shape above and below. So that's half of the wave. So they doubled that to get the wavelength. So that 0.328 is doubled. And then they can put it into C equals F lambda. They've used V here, or they've used that, but it just means the speed of sound. It's the same idea. So is equal to f lambda. So we have the lambda now, the wavelength 0.656. We multiply that by the frequency, which in this question was the 660 hertz. So you'd multiply those two together, and you end up with your 433 meters per second. All right. So last bit on that, as it says, draw a label diagram to represent the fundamental frequency of a stationary wave. So the fundamental frequency in a stationary wave in a pipe that's closed at one end. So you want the node at one end. Okay, so remember, the node is the closed part, or the pinched part of the wave. And that will be at the closed end, and then the wave starts to open up and in a Y shape, if you want to think about it from where it started. And then the antinode, the two parts, will be at the open end, and that's it. There's no other nodes. Okay, you can see there we've got -1 after that. If neither node nor antinode is labeled, so you have to write or draw them. I'll draw a quick diagram of that and pop it up with the video post. So the next bit then, to define sound intensity, again, you've just got your formula. I equals P over A. Intensity equals power over area. And you can just fill in the formula as long as you say what each thing is. All right. Last bit then on this one. It says a source emits sound in all directions. So we looked at those in some of the problems that you did earlier, or earlier on last week, and we think about it in terms of a sphere, that the sound is moving out in all directions, so in a spherical motion, so it gives you a full sound right the way around from its source. It says to describe the effect of doubling the distance from the source to an observer on the sound intensity. So imagine I'm 1 meter away from a speaker, say for example. If I double that distance, I become 2 meters away from the speaker. What happens to the sound intensity? Okay, that's what being asked here. The sound intensity measured, and then the sound intensity level. So the sound intensity measure, you can think about what's happening. If I go from 1 meter away from a sound to 2 meters away from a sound, it's obviously going to drop, but you can see here, lovely little representation. Intensity is proportional to 1 over d squared, or it's inversely proportional to d squared. So as intensity goes up, the distance decreases, or vice versa, the other way around. If the distance increases, it means that the intensity is going down, because I'm increasing that d squared value below the line, which is making the number smaller, because it's 1 divided by a bigger number. So in this case, I've gone twice as far, so you can think about it. Originally the distance was 1, and if I've doubled it, the distance can be 2, so it's 2 squared, which is 4 times smaller. So the sound intensity has gotten 4 times smaller when I double the distance. And then finally the last bit, if it's getting 4 times smaller, we can see the sound intensity level measured there. It says the idea, we talk about a decibel change of 3. Okay, so if I'm twice as far away, it becomes 6 decibels lower, because it's 2, a factor of 2 in that instance. So that's where we get those measurements from, and you guys have done problems on that as well. I'll pop up a couple of the diagrams here for this one. I'll throw up a diagram of the 2 tuning forks, and I'll throw up a diagram of the stationary wave in the closed pipe as well. Thank you very much.